Hey everyone, so today we will be looking at convolutional neural networks, which is extremely important for the purposes of a lot of different neural networks that we'll be looking at, specifically those that we apply to images and audio, but really any kind of signal is what we can use this for. So we're going to be looking at convolutions, but before we get into the neural network part of this tutorial, I do want to dig into convolutions itself. So if you have taken a signal processing class or maybe a statistics class, you've probably heard this term convolution before. A lot of people kind of skip over the history and the purpose because convolutions have existed significantly longer than convolutional neural networks. And so I just want to motivate where convolutions are coming from, what are they, why do we do them, and what is its relationship between the time and the frequency domain, or in images, the space and the frequency domain. So again, if you have already seen convolutions before because you've taken a course in signal processing, then feel free to go ahead and skip all of this and move on kind of into a later part of the video. So let's go ahead. I need to open this. All right, so what we're going to be exploring today before convolution neural networks is the convolution. And it sounds like a fancy thing, but really it's just a moving weighted average is probably the best way to express what's happening. And so I will be talking about convolutions right now in the 1D sense, so one-dimensional signals like audio, for example, instead of two-dimensional ones like images, just because it's simpler to explain it, but we will apply all of this obviously to images in just a little bit. So let's go ahead and write the formula for a convolution before we keep going. And again, this is for a 1D signal. Yn, some output, is going to be the convolution between some signal, right? This is our signal. And we're going to convolve it. This star is the convolution operator, or a typical symbol for the convolution operator. And then we convolve it with Hn. And this is our analysis filter, right? And we're going to define what all of this means in just a bit. But this operation, xn convolve with hn, has a formula, and this will look like the sum from k equals -infinity to infinity of xk h n minus k. So that's our convolution formula, and that's it. So this is obviously for a discrete convolution, because all of our signals will be discretely sampled, as most things in the real world are. There's also a continuous one where you just swap out the sum with an integral, but we won't be dealing with that today. So this is our simple convolution operator. And to motivate what this is, I'm going to show an example of a typical application of convolutions. And this could be when we reduce noise from audio, noise removal, something we have to do all the time. So let's do an example. Let's pretend I am a violinist and I play middle C, right? Whatever it looks like. So something like this, right? So we're going to play a signal, and this signal is a pure sinusoid, right? Some pure tone sinusoid. It doesn't have to be a pure tone. I'm just doing pure tone for simplicity to show what's happening. So I'm playing my violin and I'm playing middle C and I have this pure tone sinusoid. But behind me, there's a fan running, right? That can happen. Maybe it's hot where I am, so the fan is running, and we have some noise, right? Some random noise happening in the background, right? This is random fan noise. And you probably hear some of this noise in my video right now as well, but we have some random fan noise. Well, the effective audio, if I'm recording myself, the effective audio will just be the sum of these two things. And you'll end up with a signal that might look kind of like this, right? We have that sinusoid, but we also have this noisiness to it. So it's not a clean sinusoid anymore. So this is a noisy sinusoid. And my question is, can I get this back? What I want is a nice clean audio. I don't want any of this noise. So can I take this signal and get this pure tone sinusoid back? And so this is exactly what signal processing is. Signal processing is just a study of extracting the stuff you care about from signals. And in this case, we want to extract this pure tone sinusoid from our random noise. Now, there's perfect extraction, and then there's kind of approximations. And we'll be looking at some approximations today, though a perfect also wouldn't be all that complicated, but we're just going to keep this as simple as possible. So what's an intuitive method that we can think of for extracting this? Or just grabbing the overall signal that's happening, kind of getting rid of the noise. And one thing that gets rid of a noise is a smoothing / averaging filter. Right? A smoothing or averaging filter. So what would this look like? I'm going to draw this again in the case of a discrete time signal. And so let's say that this is my signal with that random noise in it. It'll look kind of like this maybe. And I'll just draw one of the humps of the sinusoid for now, right? Something like that. Let's say that's my signal, and I'll draw a couple more on this side, whatever it may be. So if we take a look, what we're going to do is create a smoothing filter. So this is our x of n, and we also will have a y, or not y, h of n, our analysis filter. In this case, our analysis filter, let's say it is, looks something like this. Let's do 1, 2, 3, 4, 5. It's going to be 5 pulses, like this. This is also known as a rectangle filter, is another term you'll see. It's going to be 5 pulses, and each of these pulses will have a magnitude of 1/5. So each of these are 1/5. Right, so each of these are 1/5, nothing too crazy. And what we're going to do is take hn and slide it across xn and just take the average. So what does that mean? What we're going to do first is we're going to, let me zoom in a little bit here to make it easier. Because we have 5, this is a 5 length filter, we're going to go ahead and line it up with the first 5 samples. So that's going to be this sample, this sample, this sample, this sample, and let's say this sample. Sorry, I didn't draw it perfectly, but you get the idea. The first 5 samples. And what we're going to do, let's call these samples x1, x2, x3, x4, and x5 is our first 5 samples. And we're going to just take the average of them. So we're going to take x1 times 1/5. So it's going to be, well, let's do it the simple way. You're going to do x1 plus x2 plus x3 plus x4 plus x5 divided by 5. Or that's the same as doing 1/5 times x1 plus 1/5 times x2 plus ... 1/5 times x5. So you're basically just multiplying each of these values by the 1/5 that we have, 1/5, 1/5, 1/5, 1/5, so on and so forth, and then adding them together. And that will effectively give you an average. And so let's undo all of this just to make it cleaner. Almost gone. Okay, good. So we're going to take these first 5 values like we had, and let's just pretend this is the average of those first 5 values. Next, we're going to take this the next 5, right? We're going to shift over by 1, right? Let's say those are my 5. So this is going to be x2 through x6. The first set was x1 through x5. Now we're going to take x2 through x6. And we're going to go ahead and, again, average it up. So that will look something like this maybe, right? We'll shift 1 over. And then again, we're going to shift over by 1, x3 to x7. Again, take the average. And if we keep taking the average over and over again, you should get something that closely approximates the kind of the average of the signal. So it'll be kind of like this, and let's say that's one of the peaks, but this will closely approximate our sinusoid, right? Closely approximate the sinusoid, and you just take an average. And that's it. That's all a convolution does. You pick your filter, just like this one, and you multiply and add. This should look a lot like a dot product, right? When we talk about neural networks again in a bit, that's what it should remind you of. We're just doing a multiply add operation. And then we just slide that filter across the signal, and it will, in this case, smooth it out, kind of removing this variability, giving us a cleaner signal, a cleaner approximation of what we think that signal is. So simple moving average is a very common example of a convolution being applied. Now, let's talk a little bit more about convolutions and why this is super important. So let's look at this example here. So what we have right now is a noisy signal. Let's just do one of the periods of the signal. And what we have also is our filter, which I'm just going to draw like this as a rectangle filter, right? So rectangle. And this is a 5 length rectangle. And I only picked 5 because I picked 5. We get to pick the filter size in the future, but for now we're just going to say it's a 5 length filter, and it's just this simple rectangle filter. What I want to mention, and this is the crucial part, convolution, I'll write this down here and then we'll kind of come back up. Convolution in time, so if we do xn convolved with hn, convolution in time is equivalent to multiplication in frequency. So that would be x of omega times h of omega. Now, if you have never seen this time frequency stuff before, there's a great video on the Fourier transform by 3Blue1Brown. I would recommend just giving that a watch and you'll have a good intuition of exactly what's going on. But I'll give you the quick rundown here. What you can imagine is in frequency, where what we're looking for is what are all the frequencies that are available in this signal. In the case of a pure tone, there's only one frequency. So let's pretend we're doing the Fourier transform, or we're doing a Fourier transform. And what we end up with is, what are the frequencies? Let's say this is 0, right? So this is going to be the magnitude of the frequency of x, because this is x of n. And this is going to be the frequency itself, which we'll just call omega. And in the case of a pure tone signal, we would just have a peak at whatever the frequency of that tone was. In our case, it was middle C, right? So we'll say MC for middle C, right? We'll have some energy at that frequency. The problem is all this extra stuff, right? We have more than just our pure tone signal. Now we have some noise, which means we're also going to have some frequency in some energy in higher frequencies. And let's just say something like this, right? We have some energy in higher frequencies. What we know is this is the signal we want. And this is noise. It's the frequency that comes from our noise. And so we want to get rid of it. So there's a couple ways we can do this. We can do this entirely in the Fourier domain. We can take the Fourier transform. We can use something known as a bandpass filter, or not bandpass, a low pass filter, and kind of cut out everything here. So we'll zero out everything else above. So it's our low pass filter. And then we can just take the inverse transform. So that'll be something like this. We can take a inverse transform, inverse Fourier transform, and this will give us a nice period, right? It'll remove all of this high frequency information. But we typically, when we do convolutional neural networks, for example, we don't typically work in the Fourier domain. And there's a reason for this, because The Fourier transform, or the discrete Fourier transform, and actually its more efficient implementation, the FFT, the fast Fourier transform, this would be an n log n operation, and then this would be another n log n operation. So the Fourier transform and the inverse Fourier transform are both expensive operations, even with the faster implementation, because n can be large, right? Audio, for example, can be extremely large. You can have an hour of audio. So how do you do n log n? It just becomes more expensive. So we have to do this, something similar, but in the time domain, right? We want to do it with the convolution. And this is where we come back to this property down here. The convolution in time is multiplication in frequency. So let's see exactly what that means. I'm going to go ahead and erase this and this, just so it's simple. And we're not doing this inverse Fourier transform. Let's take the Fourier transform of a rectangle function. So again, if you've taken a signal processing class, or if you just look online, you'll see immediately that the Fourier transform of a rectangle function is actually a sinc function. So we're going to plot the magnitude of h of omega. It's actually the sinc function. So it'll look kind of like this. It's like a decaying sinusoid, something like that. Now, what happens here? So this convolution between hn, xn, and hn, convolving these two signals, is the same as just multiplying these two. So what would that give? If we multiply these things together, you'll end up with, you'll keep most of the energy at the main, in your middle C, because it's a part of this main lobe. So you'll keep most of the energy there. But notice that we have a decaying sinusoid looking thing. The sinc function is just a decaying function. So things, as you get further away from 0, will be decayed. And you'll have much less energy, let's say, in this high frequency range, because we've decayed it or killed it. And we've kept a lot of this low frequency information where our middle C lies. Something like that. So this would be x of omega times h of omega, where this is x of omega right here. So this is x of omega, and this is h of omega, right? Our signal, or the magnitudes of them. But yeah, that's all we really care about. I'm ignoring the phase information for now. Either way, the important part is now we can take this thing here. Let's call this y of omega is this. Take the inverse Fourier transform, just like before, and we'll end up with a somewhat smoothed out, because we still have a little bit of this high frequency information. So we haven't totally killed it, because this isn't actually a low pass filter in the same way we did earlier, but it's a good approximation. But you'll have a somewhat smoothed out signal here. And that's effectively all I want to say about this. We have here, again, this is a n log n operation. This is a n log n operation. So we're saying that doing this frequency level analysis of basically taking a signal, taking its Fourier transform, taking the filter we care about in this case, taking its Fourier transform, multiplying the Fourier transforms together, or their frequency responses together, and then inverting it to get back our signal. This whole operation to get to this is done also by this. It will give you exactly the same signal. So there's no need to go through all of this hassle when we can just do xn convolve with hn. Also, this is a nm operation instead of n log n, n log, and actually this would not be n log n, this would be, let's say, m log m. Let's say this filter is of length 5, so this would be 5 log 5 in this case, but you get the idea. This is just a nm operation. And this is good because typically n is large, right? We have large images, high resolution images, or we have long audios, things like that. So n is large, but m is small. Typically m is pretty small because we only have small filters, maybe a filter size of 3 or 5 or 7, typically some odd number. So this should give you a little bit of intuition of why we're doing this, right? We're trying to do frequency analysis, right? We want to extract different frequency bands or things like that, but we want to do it in the time domain so we avoid all of this extra hassle. So let's do another example, right? This is going to be a slightly different kind of filter. What we're going to do is, let's say this is our signal. We have 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5. So this is our x of n, some signal like this. And let's say our h of n is of length 2, and it's just, it's going to be 0 everywhere, so it's just going to be at 0, it's going to be 1, and at 1, it's going to be -1. And that's it, right? So that's our hn. At 0, it's 1. At 1, it's -1. That's it. Now, if we actually take a close look, and this isn't obvious if you look at it until you study it a little bit, if you actually look, when we do xk times hn minus k, notice as we go forward in k, right? As we go forward in k, we're actually going backward on the h. So this actually, and why it's called convolution, is because we will flip h, right? We'll basically invert it before we slide it across. In the case of our averaging filter here, for example, everything is 1/5. So whether or not we flip it or not flip it is the same thing. It doesn't really make a difference to us, but we do actually flip it in the actual convolution operation. This flipping operation, again, gets thrown out the window when we do convolutional neural networks, and you'll see why later. But for now, we're going to do that. So we're going to take hn, and we're going to flip it. And so hn, and let's say, I'll just put a little tilde here for flipped, is basically -1, 1. And that's it. And what we're going to do is slide this filter across our signal, just like we did before. So let's say this has a value of 2 and this has a value of 3, right? So it's 2 and 3. So what is -1? So we're going to take these first two values, 2 and 2. So -1 times 2 plus 1 times 2. So that's -1 times 2 plus 1 times 2. Well, that's just 0. So this will produce, for this first point, a 0. Again, we're going to go on to the next 2 points. We have -1 times 2 plus 1 times 2, again, 0. We're going to do, oops, erased a little bit too much there. -1 times 2 times plus 1 times 2, again, 0. Once again, we're going to take these 2 points here. So -1 times 2 plus 1 times 2, again, 0. Right? Because we're doing, again, -1 times 2 plus 1 times 2. Nothing crazy. Now, obviously, something interesting is about to happen. There's something happening here. We're going to do this point and this point. So this is going to be -1 times 2 plus 3. Or let's do 1 plus 1 times 3. This is 3 minus 2. This is 1. So at this point, we're actually going to have a 1. And let's say this is 1. And then we're back to what we were doing before. If we do this point and this point, we'll have a -1 and a 1. So -1 times 3 plus 1 times 3 is back to 0 again. So we're back to 0. And everything after this will be 0. ... So what just happened here? And let's draw the stem here real quick. What did we just do? What did we just get from this filter? This filter looks like it extracted an edge or a place of difference. Notice how it's 0 everywhere except where the change happened. And what we store here is the magnitude of the change. Oh, sorry, this was 1. The magnitude of the change. So this filter here, h of n, is known as the difference filter, right? Difference filter. The first difference. Oh, I spelled that terribly. Let's write that again. Difference filter. The first difference filter. Where all we're doing is sliding our filter across and taking the difference of one point and the previous point, and then just keeping track of that. And it keeps track of effectively the change. This is another type of filter in signal processing. And the difference filter can be thought of as a high pass filter. Basically what you're doing here is you're only keeping the high frequency informations or the place of highest amount of change, right? So this would be a high pass filter in signal processing. But again, we're doing it in the time domain, keeping it as a convolution operation without going into the frequency domain just for computational efficiency and stuff like that. So this should give you a general idea, right? What are convolutions? What are they doing? And now the last part, the caveat. So I mentioned here before, we actually flipped the signal. But in neural networks, let's think about it this way. So we've seen 2 filters so far, but let's just look at the filter we looked at already. This is going to be 1, 2, 3, 4, 5. And all of these had a value of 1/5. Well, why 1/5? We know that we wanted a smoothing filter here. What if we treat these as coefficients instead, learnable coefficients? So why do we do this? So let's kind of keep some ideas here. This is a filter, right? Let's say this is hn. So we have some signal, right? We have some signal xn. And we're going to convolve it with hn, some filter. And this is going to produce some output. Let's call it yn. This is going to extract a specific type of information from our signal. It could be high frequency, low frequency, or something else. There's all sorts of filters you can pick out there. And the whole purpose of the signal processing study is you learn what kind of filters you need for different types of applications. But what if I do another filter? Let's say I apply another filter. Let's do in. And this produces let's say zn. And let's do another filter, right? We're applying different filters, so jn, to the same signal, which produces different outputs. So let's call this, qn. Right, we're applying different filters to the same signal, and it produces different outputs. This stuff here is typically known as a filter bank. A filter bank is exactly what you think. It's just a bunch of different filters applied to the same signal because we want to extract different types of information. Maybe we want smoothed information. Maybe we want edge information. Maybe we want a difference of Gaussian filter. Maybe there's other, we don't know. There's all sorts of filters that can be applied to your data, and which one works best kind of depends on the problem you're trying to solve. Now, in typical machine learning technique, what you would do, and this is before deep learning, what you would do is you'd apply a bunch of different filters to your images or audio or whatever, extract all sorts of different types of information or features about that signal, and then concatenate all those features together, and then pass that to some type of a classifier, like a support vector machine or a random forest, and train a model on that. A convolutional neural network changes this idea. Let's say hn is hn. Instead of being 1/5, 1/5, ... 1/5, right? Like we did before. Instead of presetting ahead of time what these filter coefficients are, what if we learn them instead? We make them 5 different weights: W1, W2, W3, W4, W5. And these W's here are learnable parameters. And so now basically we're going to ask the model to say, instead of me setting ahead of time, hey, I want a smoothing filter and a high pass filter and a low pass filter and a difference filter and this filter and that filter, instead of me providing ahead of time what the filter should be, why not train the filters as if they're linear layers, as if they're just learnable parameters? And I do say linear layers because convolutions in the actual implementation is actually just a linear layer, and we'll see that in just a bit. But that's basically the idea, right? All we have to do then is provide the model. What is the size of the filter do we want? What's the length of the filter that we want? In this case, there's 5, but it can be anything. We have to tell it how many filters do we want to apply, and that's the size of the filter bank. And once we set that, then it's just a training process, just like anything else. Just like all the neural networks we've seen so far, we just have to train the model and hopefully learn something meaningful. And this is basically what we're going to be digging into, and this is the convolutional neural network. So again, as a recap, it's kind of summarizing everything. Convolutions are just a moving weighted average. They're nothing fancy. And this is your convolution formula. And typically, in the purposes of a convolution, this h, we flip it and then slide it across our signal x. And this flipping operation is it's why we call it a convolution, and you can read about it more online. I won't go into more detail about that. But in the case of a convolutional neural network, if we are learning the filter, then whether or not we flip the filter doesn't actually affect anything. So in most implementations of a convolutional neural network, if you go look at like the Cuda implementation or anything like that, you'll see they actually just don't flip. Because if you're learning anyway, then it doesn't matter whether or not you flip it or don't flip it. It'll just learn it on its own, so it's not a big deal. And so signal processing, like I said, it's basically the science of extracting stuff you care about from signals that's full of noise and other stuff. Right? So signal is full of noise here, and what we're trying to do is extract the sinusoid from this noisy sinusoid because there's a fan in the background. And one technique to do this is a simple smoothing or averaging filter, which is exactly what you think. It's just a rectangle filter, nothing fancy. In this case, it's a 5-length filter, so each value has a 1/5 coefficient value. And we just, like we said, we just multiply and add, and then slide by 1. Multiply and add, slide over. Multiply and add, slide over. And we repeat that over and over again until we've effectively smoothed out our signal. And this convolution operation allows us to do frequency level analysis, such as I only want to keep the low frequency information and throw away the high frequency information. It allows us to do this without ever actually stepping into the frequency domain. We can do the entire operation in the time domain or the space domain in the case of images. And this is important because you can see all these n log n's, n log n's, m log m's, all expensive operations that we want to avoid doing. Rather, we can just stick to convolutions, which is simple nm, nothing crazy. Once we have done the convolution, again, we looked at a second example here. This is an example of a smoothing filter. This is an example of a difference filter. So this keeps the high frequency information. Where does the change occur? And the entire purpose of a convolutional neural network is, A, we typically want lots of these filters applied to our signal because we want to extract different types of information from our signal. So that's important. So we have something known as a filter bank. And then the second step is, well, instead of me deciding that I want this filter and this filter and this filter from a textbook full of all the different filters I can pick from, why not let a neural network train and figure out what these filters should be and just set these as learnable parameters? And that's basically it. That's our entire setup for the convolutions, what convolutions are. If you made it this far, that's great. Hopefully this was helpful to see. Obviously, this is a very high-level overview of more complicated signal processing topics. There's a lot more depth here that I didn't go into. But if you take a signal processing class or look on YouTube, there's tons of signal processing courses there that you can look at, then this should make a lot more sense. So now, let's go ahead and begin our exploration of convolutional neural networks and their actual applications. So we're going to be moving from 1D to 2D signals now because we'll be working on images, but all the principles stay the same. So here, right, so previously we actually trained a dense linear neural network for MNIST, right? This is the model we wrote. Nothing crazy. We're just going ahead and flattening our image and then running it through a bunch of linear layers. And this first linear layer had a 28 by 28 input because our images were a size 28 by 28. So we just treated it like a basically a feature vector for every image that's just made of the pixel values. First of all, this has one obvious problem. What if our image was really big, like 1,000 by 1,000? That would be 1,000,000 inputs to the first layer of the neural network, and that's not good. Right? That's too much compute, and this doesn't scale very well at all. The second culprit is we're throwing away spatial correlation, and here's a good idea. So here's an image. Here's the digit of a 1, right? And our goal is to train a neural network to predict this. Predict that this is a 1. But notice that when we take this image here and flatten it, all that information is lost, right? If I gave you this feature vector by itself, this 1D vector, you could not tell me what this is that easily. You can't just look at it and say, oh, that's a 1. On the other hand, this is clearly a 1. And so this conversion from 2D to 1D really messes up what we're trying to do. And this is exactly why we need to use something like a convolution that does this. And this is the typical way you're going to see convolutions. So this is a 2D convolution. And let's define a couple of different things here. So the first thing is, notice this filter, the dark gray area. It is a 3 by 3 filter. So this is a 3 by 3 filter, so it's a 2-dimensional filter. Previously, we were just looking at 1-dimensional filters. So it was just like a, like just of length 5, and that's it, because we're going to apply it to a 1D signal. In this case, it's a 2-dimensional signal, so our filter is also 2-dimensional. So this is a 3 by 3 filter, and all we're doing is a multiply accumulate. Basically, whatever this filter overlaps with, we multiply with the values that it overlaps with, add it all together, and that becomes this new value up here, and this is our convolution operation. And so convolutions have just a few things that we need to provide it. The number of input channels, the number of output channels, the kernel size, the stride, and the padding. So the number of input channels is just determined by your data, basically. If you have an RGB image, for example, then you have 3 input channels. If you have a grayscale image like MNIST, then you have 1 input channel. The output channels is the way they explain it. It's really it's the number of channels we want to expand out to, but actually it is the size of the filter bank. How many filters do we want to apply to our signal? And we'll see how that works out a little bit later. The kernel size is completely up to you. What's the size of the filter that we want? The one we saw above was a 3 by 3, but you can pick anything you want. A rule of thumb, though, is we typically pick odd number filters, so there's an actual center. It's not that even numbers don't work, it's just awkward. So we typically stick to odd number filters, odd size filters. We then also pick the stride and the padding. So the stride is how much of the filter move in every iteration. Notice here that the filter is basically moving over by 1 in every iteration. We can also move over by 2 or 3 or whatever else we want, and we'll see what effect that has on our signal in a bit. And then padding is how much border we want to put around the edge of the image, and we'll see why we do that in a little bit as well. But a good example of a filter actually is the Sobel filter. So if you haven't heard of a Sobel filter, it's effectively just a edge detector. So we already saw the difference filter, for example, as a edge detector. The Sobel filter is exactly the same. It's an edge detector just for images. So if you take an image and apply the Sobel filter to it, notice that you basically end up with another image just with the edges outlined, and everywhere else is darked out. Because anywhere there's no change, the Sobel filter will not detect an edge. And so we're effectively applying this convolution operation of this filter and this filter, the first one detecting edges in the x direction, the second one detecting edges in the y direction. And we're applying these filters, convolving them with our image, and then putting them together to produce this. This means that if we do both of these filters, it'll give all the edges in the x and the y direction, and this is kind of like a filter bank then, right? We have 2 different filters extracting 2 different types of information from our image, and when we put them together, we get this. So what is the typical convolutional neural network structure? We'll be digging into this picture a little bit more later. So for now, let's just keep it simple and get all of our imports in. So what we need is import torch, import torch.nn as nn, import torch.optim as optim. We need from torch vision import transform. So we haven't actually seen torch vision yet, but PyTorch has a package that does a lot of the vision stuff that we're going to care about. So we're going to use them. We need from torch.utils.data. We need a dataset and data loader. There we go. And we need from torch vision.datasets import image folder, which is what we're going to use to actually load our cats versus dogs image in the future. We need from tqdm.notebook import tqdm. And lastly, we need to import numpy as np. And I'm also going to just throw a filter warnings in here because I think there's one small bug or issue that we don't care about, and I don't need it to print it out. So there we go. Great. So that's the setup for everything. And so let's go ahead and just try a convolution, see how it works in PyTorch, and then everything else should go pretty quickly from there. So what we're going to do first is we're going to create a random image. We're going to do rand is equal to torch.rand n. We're just going to create a random tensor, just rand, not rand n. We're going to do batch size by 3 by 128 by 128. So this is the typical shape that you see your tensors in for images. We have a batch size 4 by the number of channels. You know, in this case, if we have an RGB image, for example, then it'll be 3 by height by width. So 4 by 3 by 128 by 128. And let's go ahead and define a convolution and see what the output looks like. So we're going to do conv is nn.Conv2d. That's how we define if we want a 2D convolution, that's how we do it. Conv1d will give a 1D convolution, which is what we typically use to process audio. Conv3d is something we need for volumetric data or for like video data and things like that. But because we're working on static images, we're doing conv2d. And we have to provide it in channels, which is going to be 3 because we have 3 input channels in our data. Let's do out channels as 3 as well for now. Kernel size is up to us. Let's say 3 as well. Stride is 1 and padding equals 0. So that's our convolution. And we're going to go ahead and apply this convolution to our rand. So we're going to do conv rand dot shape. So let's notice a couple things here as we kind of change. The batch dimension will stay the same because it's parallelized over the batch dimension, right? So we don't worry about that too much right now. So we have batch of 4. Our number of input channels was 3, and the number of output channels was 3. So nothing changed there. And actually, to make this simpler, let's just do 1, right? 1 output channel for now, and we'll see why later. Then we have a kernel size of 3, and that produced, notice how the image got slightly smaller, right? Some compression happened of our image. And this is something that convolutions always do. Convolutions will compress the image. And why does that happen? If we go back to our image up here, right? Notice our original image was a 4 by 4, but the new image is a 2 by 2, which means some compression happened in the spatial dimension of the image. So now that we have that, we can go ahead and try to play with this a little bit. And we'll leave the out channels alone for now. And we'll get back to what this actually is doing a little bit in the future. If we made this a different input channels, this will throw an error because this is saying, hey, I expected 5 channels, but I got 3 instead. So that's obviously not good. And that just makes sense because we have 3 channels here, so we have to leave this as 3. If we change the kernel size, let's say to 7, we'll have a slightly larger downsampling of our image, which makes sense because we've just done more downsampling. So there we go. The filter is larger, so you're covering less space. Let's put this back to 3. Another way of downsampling is changing the stride. Let's say that we change the stride to 2. Now we have a significant reduction in our size. And so let's take a quick look at some of these GIFs, which I think are really helpful to see visually what's going on. And so yeah, these are some incredible animations. So this is one we've already seen, right? No padding, no strides. Let's look at one with strides. So no padding, but strided. Notice that it's moving over 2 at a time here instead of 1 at a time. So you have a smaller image, right? It does more downsampling. Padding, notice how padding, we basically add, there's a couple different types of padding. The most common is 0 padding, but there's also reflect padding and other stuff, but we're gonna stick with 0 padding for now. Notice how padding allows the filter to spill over the edge of the image just a little bit, right? Unlike here, notice how we're stuck to the image itself here. Here we're allowed to spill over the edge just a little bit. And so these are kind of the things that you want to care about. And so we have, the main thing we care about is stride, but padding is there as well. But we're not going to worry about it too much about the details of that. So padding, the stride is kind of the typical way we do this. If we do both, if we change the kernel size to 7, well, we get slightly more downsampling, right? It became a little bit smaller. If we make the output channels, let's say we make it 128. Now the 128 comes to here. Effectively, it is our final output of how many output channels we have. But more importantly, it's actually the number of filters we have in our filter bank. And that's what I want to talk about now. So we'll be seeing this a little bit about how convolutions are just matrix multiplications. So we'll come back to this in just a second, but I just want to explain what's happening here. Notice how a convolution on a 3D filter actually works like this. On a 3D image actually works like this. So what we have here is let's say an RGB image. So an RGB image will look like this. We'll have a height and width, but we'll also have a little bit of depth, right? Something like, so this is going to be height, width, and a depth of 3, because there are 3 channels, right? There's an R channel, G channel, B channel, RGB. So I'm going to flatten this out real quick and just draw it like this. This is our R channel. This is our G channel. And this is our B channel. Actually, it'd be better if I wrote this above. R, G, B. And let's say these are 3 by 3 images, just to keep it simple. So there we go. Draw all of this out. There we go. And we're going to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. All right, so these are my, let's say these are my values. So like we saw in the convolution, if we go back here, notice how it's sliding across, but it's also not across space, but also across the channels, right? We're sliding across everything. And so let's say we're doing this chunk here first. This is a 3 by 3, so let's say we're doing a 2 by 2 filter. So it'll look something like this. And so this region is what we are filtering out. I know this looks a little weird, but something like this. Right, and then this will go in back there. So this block is what we're doing, which is actually just this block here. Right, this stuff right here. So that'll be the first one. So this is our RGB channel. This is me just drawing it out, flattened out. So in this case, right, just to keep in mind here, our filter is 2 by 2, but there's 3 channels, which means this has 12 learnable parameters. Right? 12 learnable parameters. And so we end up with a 2 by 2, that's our filter, and this is the number of input channels in this specific convolution. Now, this is filter 1, right? Filter 1. And so how is this going to work? We're going to take our 12 parameters, so that's W1 through W12, and we're going to multiply, right? First we're going to do, the first one will be W1 times 1, so it'll be 1 times W1 plus 2 times W2 plus 4 times W3 plus 5 times W4, and then we move on to the G channel, plus 10 times W5 plus 11 times W6 plus 13 times W7, terrible 7, plus 14 times W8 plus ... Or I guess I can write the last one. So plus 19 times W9 plus 20 times W10 plus 22 times W11 plus 23 times W12. Right, so this is the dot product we're doing. We're multiplying all this together, and this is going to produce a single number, right? This entire operation will produce some number, and we can call it A. And so this will produce A. Let's say our output is here. We can see that there's going to be, after we do this convolution, it'll be 2 by 2, right? Because we have this one here, and then we slide over by 1, and then we slide down, and then we slide over by 1 again. So the final output will be something like this, A. And let's say the next output, when we do the slide it over by 1, let's say it's B, slide it over by 1, C, slide it over by 1, D. Let's say this is the output of this convolution. This is a 2 by 2 by 1. So this is a 2 by 2, or in the case, how we care about 1 by 2 by 2. Number of channels, 1 channel, and each channel is 2 by 2. That's my final output of this convolution operation. But this is with only a single set of 12 learnable parameters. So this is 12 learnable parameters. What if I do another filter? So let's say filter 1 it'll have 12 parameters. Filter 2 has, again, 12 parameters, because all of them are the same. But it'll be this will be a different 2 by 2 by 3 filter, 2 by 2 by 3 filter, and then ... We can have filter, let's say K, 12 param, 2 by 2 by 3 in this case. So we have a bunch of filters, and we're going to have a bunch of learnable filters, each with 12 parameters that are all applied to the same image. So the first one will produce like AB, let's say A1, B1, C1, D1. And then the second one will produce another one, right? We'll have A2, B2, C2, D2 from the second set of filters. So this is filter 2. And this is filter 1. And then we're going to have another one, ... And you'll go down to filter K, which will produce, A, K, B, K, C, K, D, K. So what we have is K different outputs from K different filters applied to the same original 3-channel image. And if we stack all of these together, you'll end up with a final output that looks like this. It'll be a 2 by 2 of A, I, B, I, C, I, D, I for however many there are. And there will be K number of filters, or K number of outputs. So what did we do? Again, as a recap, we passed in a 3-channel, and each image is 3 by 3. So there's 3 RGB channels, and each channel is 3 by 3. each channel we apply k different filters, and we convolve them with each of these channels. And again, all of these filters are learnable, and we're hoping different filters applied to the same image will learn different types of information from the data. Some will learn, some will be smoothing, some will be averaging, some will be edge detection, some will be all sorts of filters, or something that we can't parameterize that easily. So we have k filters, which means now the output of the k filters, each filter outputs a single channel of a 2x2 signal or output image. And then we stack all these together and we produce k of them. And so the reason we have k output channels, or when we say output channels, that really means we're applying k different filters, or applying a filter bank of k filters to our image to produce those k output channels. And that's it. That's the big idea behind multi-channel convolutional neural networks. So let's go ahead and take a quick look now at the step. Okay, yes, exactly. So first step, right, before we kind of keep going, one thing to keep in mind is we can actually calculate the size of an image after a convolution. So we saw here, this is 61 right here. When you take a 128 by 128, apply a kernel size of 7 with a stride of 2, we end up with 61 here. We can actually calculate this ahead of time because we have the formula, which is this. This is the formula. If you look on the PyTorch convolution, so let me actually pull that up now. So nn.Conv2d, the PyTorch documentation for the convolution. You'll see here, they give you the formula right here, right? It's a floor function, and then you just have some extra information. We didn't talk about dilation. We don't really need to right now. I think it's a little overkill. So for now, we're just going to be sticking to what we've seen so far. So there we go. We have our convolution set up, relatively simple to use, nothing too crazy. And another important part is we want to be able to stack convolution. So I'm just going to copy this in, right? Because what we're doing is we're extracting some features from an image, and then we're going to extract a higher level of features from those images. And the intuition here is exactly like neural networks. Deeper neural networks can extract more complex features from your data. And so for the same reason we stack linear layers together for more learning capacity, we also stack together convolutions. And so notice here we have, let's throw the batch size in there. We had the first convolution is a 3 by 32, 3 input channels, because we have 3 input channels here. I specify I want 32 output channels. That means there's 32 unique filters being applied here. I want a kernel size of 7 with a stride of 2 and a padding of 1. It's my decision. The second convolution, and this is key, the first convolution is going to output 32 channels, which means the second convolution will input 32 channels. And then I say again, I want 64 output channels. And then I want a kernel size of 3, stride of 1, padding of 0. And this is the effective output of stacking those two convolutions together. Now, something to keep in mind, convolutions are linear operations, just like a linear layer. It's an affine transformation. All you're doing is multiplying and adding numbers together, just in a slightly different way, because you're multiplying and adding on different pieces of your image. But regardless, it's still multiplying and adding, which means stacking two convolutions together is still just a linear transformation of some sort, just a slightly different type of linear transformation. So this would not be a very powerful model. So for the same reason we insert activation functions to inject nonlinearity into our model in the purposes of linear neural networks, we also want to inject nonlinearity or activation functions in between our convolutions. And we're going to see some of that in the future. For now, though, I do want to discuss how convolutions are actually just matrix multiplications. So again, this part is a little bit overkill. If you're not interested in it, then you can skip over it. But what I want to talk about is the im to call algorithm, or nn.Unfold is how PyTorch calls it. So convolutions, as we saw here, this operation you're seeing here, as we're sliding the filter across the image, so on and so forth. This seems like a slightly expensive operation, right? There's some for loops involved and that sort of stuff. And we don't really want to do that because in Cuda, we have super optimized kernels that already do high performance matrix multiplication, which is great, right? What we want is high performance matrix multiplication, something that's fast, because everything about this stuff is expensive. These are big matrices with big matrix multiplications with big kernels and big images. So we want this operation to be as efficient as possible. And so doing it as a convolution may not necessarily be the fastest. And so there's a bunch of ways of doing this, but PyTorch decides to use the im2call algorithm, or nn.Unfold, to effectively convert this problem to a matrix multiplication problem. So this should look very familiar to what we just did. But instead of just doing this operation the way you're seeing it here, we're going to first reshape this data and unfold it, or do the im2call. So what you're seeing here is the first set of convolutions will be 1, 2, 5, 6, 17, 18, 21, 22, you can't see them, but it's behind. And then 33, 34, 37, 38, which is back here, right on the top left. So we're basically doing the top top corner square of all three channels. And notice those numbers, basically we just populated here, 1, 2, 5, 6, 17, 18, 21, 22, 33, 34, 37, 38. So these 12 values here are just the 12 values in this tubelet kind of right here. And then similarly, we slide over by 1 and you get the next set. And then we slide over by 1 and we get the next set. And we just do this over and over again. And all we're doing is taking the data and just copying it into this matrix, where the length of this, or the number of rows we have, is the filter size. There's 12 values here because this is a 2 by 2 by 3 filter, as you can see here. And there's 9 patches in our image, right? There's 9 possible windows in this image, as you can see. And so formatting it this way now converts this to a matrix multiplication problem, and I can show how that works out by simply implementing it, and that should make it simpler. You can also read through this on your own, which basically just talks about what I'm about to implement, but I think it's easier just to do it that way. So what we're going to do is class myConv2d nn.Module, and def init self, just like before, and we have in channels, out channels, kernel size, stride equals 1, and padding equals 0. So these are the typical inputs we provide the PyTorch Conv2d. So that's where we'll be using this as well. And so we need our super myConv2d self.init. There we go. And so let's just go ahead and store everything. Self.kernel size is kernel size. Self.in channels is in channels. Self.out channels is out channels. Self.stride is our stride, and self.padding is equal to our padding. So we're just going to go ahead and store all these as class attributes. Now that we have that, what we're going to do is reformat our convolution operation as a linear operation using a simple linear layer. So we're going to do self.linear, self.linear is nn.linear, and the input will be in channels times the kernel size times the kernel size. Now, why is this the case? Why is it in channels by kernel size by kernel size? Exactly why we had it here, right? Our kernel size is 2 by 2, and the number of input channels is 3. So a 2 times 3 is 12. And so in this case, 3 times 2 times 2 will be 12. So there we go. That's our kernel size. The number of outputs will be the out channels. And you'll see why that works out to be later. But this is effectively us having a bunch of layers that go from, let's say this is 12 in. Let's pretend this is 12 input. 12 input, 1 output, right? The regular convolution operation, just like we saw earlier, what we saw here, is it takes in this case 2 by 2 by 3, just like before. So it takes in 12 input and produces a single number A1. And that's it, right? It takes in 12 numbers, 1, 2, 4, 5, 10, 11, 13, 14, 19, 20, 22, 23, multiplies it all up with all of the weights that we have, and then it all becomes A1. But we don't want just A1, we want A1, A2, all the way up to AK, right? For K different possible output filters, right? We want K output filters. So if you want K output filters, instead of just outputting one output, why not output K of them? So in our case, we have 12 inputs, and we have however many outputs we want, which is the out channels. So there we go. That's our linear layer. And now what we're going to do is def forward self x, and let's create some random data. Rand is torch.randn. Let's do batch size of 4 by 3 by let's do 128 by 128. And our conv is going to be, let's call this my conv, is going to be my conv2d. And in channels is 3, out channels, let's say, is 64. Kernel size, let's say, is 7. And we'll leave everything else as is. Looks like I missed a, oh yes, so we can just put a pass in there and we should be good. Yeah, good. So step 1, we're going to keep track of the shape of our data. So batch size by channels by height by width is equal to x.shape. And we need to make sure that channels is equal to our self.in channels. If this is not true, then something has gone wrong. We expect that if our model is expecting this number of input channels, or 3 input channels, then our data better have 3 input channels. So there we go. And we can actually apply my conv to rand. There we go. So step 1 will be converting our image into the patches, right? Into patches. And this is the im2call or the nn.Unfold that PyTorch has. So we're going to do patches is going to be equal to nn.functional.unfold. And in unfold, we provided basically the same information our convolution cares about. What is the tensor we want to unfold? Our kernel size is going to be equal to self.kernel size, right? What is the kernel size we care about? Stride is going to be self.stride, and padding is equal to self.padding, just like that, right? We're just providing the information that we care about for our convolution, so we're just going to go with that for now. Now, if we look at print patched.shape, notice here, what we have is batch size of 4, so we can ignore that. We have 147 by 14,884. So where did all these numbers come from? Well, 147 is going to be, notice our kernel is a 7 by 7 kernel. So it's going to be print 7 times 7 is 49. And there's 3 input channels. So if you multiply this by 3, you will get the 147. So there's 147 filter values in this thing that we'll be multiplying our filter by. So we have 147 patches or values in every patch. Where did the 14884 come from? This has completely to do with our convolution itself. So that's basically this. How many possible patches can we do? With the setup we gave it with the stride of 1 and a padding of 0, well, these are the possible sliding windows that we have. But we can reduce it, right? If we do a stride, let's do stride equals 2, we'll have significantly less, right? Much less number of number of patches. We've done much more downsampling of our image. So that's fine for now, but we're not going to do any strides. We're going to leave it at this, so it's clear. So this is our data. This is our tensor now. So how do we work with this? This on its own is not helpful. We need to make this the last dimension. Remember a linear layer, so our linear layer, this will also be 147. So if we print self.linear, 147 in, 64 out. So this linear layer here expects 147, which means 147 needs to be the last dimension. So if we print patch.shape, it needs to be the last dimension. So let's do patch is equal to patch.transpose 1, 2, print patch.shape so we can see it happen. So we just flop those two dimensions, nothing crazy. And then what we want to do is just expose the dimensions that we actually care about. So we're going to do dot, here we go, dot reshape -1 by self dot in channels times self dot kernel size times self dot kernel size by, and let me double check that I'm indeed doing this correctly, because I always get the shape slightly wrong. Yes, exactly. So we're going to do this kernel size times, and I think that's it actually. Yeah, so there we go. So all we did is flatten on the batch dimension, right? So let's get rid of view for a second so we can compare. What we had is a 4 by 14884 by 147, but what we really have is 4 images with 14884 patches. That's in each image, and then 147. So we can go ahead and flatten these two because the convolution happens independently of every patch. Every patch we just convolve it independently. So we can put these two dimensions together. So let's put it back, and we end up with something like this, basically flattening those last two dimensions. Now that we have this tensor set up, we can go ahead and actually do our convolution. So we can do conv output is going to be self.linear patched, TCHED. And we can see our print conv output.shape looks like this. Oh, must have spelled patched wrong. There we go. Looks like this. 59, 536 by 64. Right, so we went from 147 to 64. That's our linear layer after all. So there we go. That's the actual convolution occurring in a parallelized way. Now that we have that, we can go ahead and put our data back in the format that we care about. So we can do conv output is going to be conv output dot reshape. We're going to do batch size, so that was 4, by 64 will be the new number of channels, but actually we don't get the 64 just yet. So we're going to do -1 by our conv output dot size -1. So there we go. So if we look now, so we got the 4 by 14884 back. Another way we could have actually done this, which might be a little bit clearer, is we can do, let's just do it here, print, oops, here we go, patch.shape. So we had, actually it'll be before this, patch.shape. So these here, so we can do, we don't care about the batch size here, but we do care about the kernel filter, or let's do kernel param size by num patches is equal to patched dot shape. There we go. So this will go ahead and store our kernel param size 147 by 14884. So we have all that information. And then in this final output, we'll do batch size by num patches, because remember, we flattened batch size and num patches together, right? This -1 flattened those dimensions. So we just want to separate them out again, back to batch size by num patches, and then we can actually make u -1, just for simplicity. There we go. So now that we have that, we have effectively performed our convolution operation. Now we just need to put it back how we found it. So one thing we need to compute is the output height and the output width. We already know what the formula for this is because we have it written up here, right? We know exactly, given a convolution input with some padding, some stride, and some kernel size, what will be the final shape of that tensor. So we can go ahead and do that. So the conv height will be just, it'll be, let's say it's height, which will be this height right here. Height plus 2 times self dot padding, how much padding we added, minus self dot kernel size divided by self dot stride plus 1. And then our output width will be identical, right? Output width will be the exact same formula, it's just for the width instead of the height. Again, if we're not dealing with square images, then this matters, but because our images are square, we don't really care too much. But this will just be width. There we go. And so we can then go ahead and wrap this up. Our output is going to be the conv output dot transpose 1, 2. We're transposing again because, let's print it out, print conv output dot shape. We want it to be 4 by batch size by channel 64 by whatever is here. So we just need to go ahead and actually put the channels in the beginning. So this will do, stick it down here so we can see it, print output dot shape. So that just puts the channels right there. And then we can do dot reshape. And in here, we're going to do batch by self dot out channels, what we know it to be, by output height by output width. And this isn't batch, but batch size. And there we go. We have a 4 by 64 by 122 by 122. So batch by channels by height by width. And notice a slight downsampling has happened. So the key to this whole thing is just using the PyTorch Unfold. But this just gives you an idea of how the im to call algorithm can be used in PyTorch to write your own custom convolutions if you have some different idea that the regular nn.Conv2d does not incorporate. And again, just to test this, torchconv is going to be nn.Conv2d with 3 input channels, 64 output channels, and a kernel size of 7. And so we can do myconv.rand.shape, and we can do torchconv.rand.shape. And we'll notice they are identical to each other, the shapes of them. Obviously the values will be different because these are different filters and these were randomly initialized differently, but the general principle is identical. Either way, that kind of clears up, hopefully, everything you need to know about convolutions, which is super important. Let's go ahead and now talk about the last couple things. This should go a little bit quicker now. But the last couple things we need before we actually implement a convolutional neural network. The first one is pooling, right? So pooling convolutions, as we see, are relatively expensive operations, and especially when convolutions were being first researched, that level of compute wasn't easily available, right? It took some effort. So we needed to do some kind of a pooling. And pooling is exactly what you think. Instead of convolving, it looks very similar to a convolution, but instead of doing a regular type of convolution, we do something called like a max pooling or an average pooling or something like that, where we're effectively doing the same operation here, but instead of some learnable 3x3 filter, it's just some function. And the function could be, if it's max pooling, we're going to slide our filter across our image, and we'll grab the biggest value out of these 9 values in this 3x3 grid and just stick it up here. So that would be max pooling. Average pooling is exactly the same thing, except instead of describing the max, you'll just take the average of these 9 values and put it here. So there's all sorts of different pooling methods. Max pooling seems to be very popular for image processing, so we'll be using it. But for now, we do need to talk about one thing, and this will be our pooling versus adaptive pooling. So let's first do pooling and go from there. So we're going to do rand is equal to torch.randn. I'm going to do 3 or batch size of 4 by 3 by 128 by 128. So average pool is equal to nn.Average pool 2D, because again, this is a 2D pooling. There's also 1D and 3D, but we're doing 2D. Kernel size is 3, right? Average pooling. Looks just like that. Now in average pooling, by default, the kernel size and the stride are the same. But that doesn't necessarily have to be true. We can change that, but let's just go with, let's create a second one, for example, nn.Average pool 2D. Let's do the kernel size is 3, but the stride is 2. So now we have average pool 2, right? So we've just changed the stride. You can also add padding, right? There's all sorts of stuff you can do. And we're going to do out is average pool rand, and out2 is average pool 2 rand. If we print out.shape and out2.shape, notice that we had more downsampling on the first one because the kernel size and the stride were 3, where we reduced the stride on the second one, so the image space is slightly bigger. But pooling is a really effective way of compressing and downsampling your image without doing an expensive convolution. Pooling is very cheap to do because max pooling and average pooling is simple, and backpropagation for max pooling and average pooling is also very simple. So that's why we like them. But one thing that we will use actually more often than just pure pooling is adaptive pooling. And adaptive pooling is exactly the same thing, but it's slightly reversed. So in the case of an average pooling, we provided the kernel size, the stride, the padding, that sort of stuff. But what if we want our image to be a very specific shape? So for example, notice this, let's say we went from 128 down to 63. What if I wanted it to be 64? What stride and kernel size do I have to pick here? And if I do figure it out, so if I maybe add a padding equals 1, there we go. That produces a 64 right here, which is the shape that I want. Now, if I change my image, for example, like let's say these became 120, right? I'm testing different things. I make this 120, and I want this to be 64 again. Well, okay, I could fiddle with this maybe. Oh, looks like that throws an error. You could fiddle with it, right? You can fiddle with it and probably get it to work. And what I'm saying is we don't need to fiddle with it. We can do adaptive pooling. So in adaptive pooling, instead of setting the kernel size, stride, and padding, we just set what's the output size we want, and PyTorch will figure out what the kernel size, stride, and padding is. How does it figure out? Well, we know the formula. We know exactly how to do it. So it's not all that complicated. So we can do, for example, adaptive pool is going to be nn.Adaptive average pool 2D. And in here, we're going to provide it that I want a 64 by 64 output. Specifically, I want a 64 by 64. So I want my 120 by 120 to be downsampled to a 64 by 64. And, well, it'll do it for you. We can do adaptive pool, rand, and let's print out the shape, actually, rather than all this, dot shape. And there you go. It has figured out what it needs to do to pull it down to a 64 by 64 specifically. And that's it. Nothing too crazy. You'll see this comes in handy at the very end of our convolutional neural network. So we'll kind of keep it there. Next up, batch normalization. So batch normalization actually did not come out when AlexNet was there. This came out later on, but is an extremely important part of neural network training. And as you can see, there's actually a bunch of different types of normalization: batch norm, layer norm, instance norm, group norm. Batch norm seems to be pretty popular for most neural networks. Layer norm is extremely popular for transformer-based neural networks. Group norm seems to be very popular for a lot of the diffusion stuff and a bunch of other things out there. So each of these normalization techniques have kind of found their way, but batch norm actually is the best method of normalization. But there's a caveat. All the other normalization methods are trying to approximate batch norm. So let's kind of take a look at why we do batch normalization. We've seen before, right? In neural networks, we like, and actually not just in neural networks specifically, we like to normalize our data. Right? Data being normal is super helpful for the purposes of neural network training. Now, why would this be the case? And this has to do with the activation functions. So we know that if you have a normal distribution, for example, right, a normal distribution, and if you apply some affine transformation to it, some linear transformation. So we're going to be doing some matrix multiplication with A, and you might add a constant to it. This will produce another normal distribution. It just might be shaped slightly differently. It might be shifted over, that sort of stuff. But a linear transformation of a normal distribution will just produce a shifted and scaled another normal distribution. Nothing crazy. So in our neural network, right, how do our neural networks typically work? We have, let's say, y is going to be a, so we're first going to do w, let's say, weight 1, x plus b1. This is the first linear layer. We'll then apply some activation function to this, and then we'll multiply this by w2 plus b2, right, for the second linear layer in our model, let's just say. So, well, no problem. When we have some data, right? We have some data x, and let's say x has already been normalized. We've already done the hard work of normalizing it. And this is, if you've used scikit-learn, this is your, just z transform or standard scalar or just normalizer. We've just normalized x. It's no big deal. And we can do this because we've calculated the mean and standard deviation of x ahead of time, right? We've already done the hard work to do that. So x is nice and normal. So w1 plus b, w1x plus b, this whole thing, so if x is normal, then x times w plus b is also normal. No problem there. Now here comes the problem. Sigmoid, right, is a non-linear function, right? There's no point of having a linear activation function. These things are non-linear by default. And so if we apply a non-linear function to a normal distribution, we no longer have normal data. It's not possible. So for example, let's say we have a standard normal distribution centered at 0. And we apply this to the ReLU activation function, which just looks like this, right? 0 everywhere under 0 and left alone above 0. Well, if we apply these distributions, if we apply the ReLU function, ReLU, to our normal distribution or data that's normally distributed, you'll end up with something like this, right? Anything under 0 will become 0. So let's do it in pink. Anything under 0 will become 0. And then anything above 0 will just be left alone. And this is most definitely not a normal distribution. And all sorts of activation functions can mess with our normalized data. This means this next set, W2 plus B2, and remember, W2 and B2 also have to be optimized, just like W1 and B1, via the same backpropagation mechanism. W2 and B2 are being fed not normal data. And this is a problem. It hurts with convergence. It hurts normalization. It typically just hurts training in general. So how do we deal with this? What if we, so batch normalization is a technique of what if we renormalize after sigmoid? Just renormalize the data. But now the question becomes, if we want to normalize our data, we need two things. We need mean and our standard deviation, right? These are the parameters we need to calculate for the purposes of normalizing our data. How do we normalize our data if we need to calculate, the question basically becomes, I know the mean and standard deviation of x because that is my data. Do I know the mean and standard deviation of x times something plus something and then through a activation function? No, and I especially don't know because I don't know what W and B are. These have to be trained. I don't know what they are. So how do I compute mu and sigma? Well, it's very simple. We estimate it. Estimate from batches. Estimate from batches. Right? We're basically passing the neural network batches of data. So why not try to estimate what the mean and standard deviation would be at that point in the model by computing the mean and standard deviation? Now there's two caveats here that needs to be done, right? The first one is if we're estimating from batches, we need large batches, right? And this is your typical thing about population statistics. If you want to compute a mean and a standard deviation that you are confident in, then you need large samples. If you're trying to find the average grade on something and you only took an average of 2 or 3 of your students, you wouldn't feel very confident about that. On the other hand, if you took the average of maybe 200-300 students, then you would feel confident about that. So you need large batches for a successful batch normalization. Otherwise, this doesn't work out at all. And the problem this causes is for big models, we actually cannot train with big batches. Right? Because we just don't have enough GPU memory available to us to do this. The second problem is if we use multiple GPUs to train our model and we're passing batches to multiple GPUs, all the GPUs need to synchronize. We need to compute the average across all the GPUs, not just one of them. And this synchronization step is very expensive when doing multi-GPU training. This is why batch normalization is typically approximated via other methods that are layer norm or group norm instead of batch norm. And we'll talk about layer norm and group norm in more specificity when we implement transformers in the future. But for now, that should give you an idea. Basically, we've applied some nonlinear function to normalize data, so our data is now no longer a normal distribution, which means future parts of the neural network will not be that happy and will not be as robust and could also fail to converge as quickly. So that's basically it. So we're going to have to use batch norm. Batch norm is super simple. Again, in PyTorch, we basically use nn.Batchnorm2d because we're dealing with a 2-dimensional image, and you just provided the number of features. And the number of features in this case is just the number of channels in our data. The last thing to talk about is dropout. And so we've talked a little bit about overfitting, right? So neural networks have a tendency to overfit because they're very expressive, large models that can learn relationships, but they may not be learning relationships, but rather just memorizing your data, which is a problem. So it's memorizing, not generalizing. We've talked about this. And so the problem here is that if you're just memorizing your data set, and your neural network's not learning anything meaningful, then you can't really use this model. And it typically does not work well in the real world. So there's a couple of techniques we use for regularization. The first one being regularization, weight regularization, though I won't go into too much detail about that right now. The second one is dropout, where we randomly delete parts of the model in the forward pass. So the way you can think about this is the neural network, when training, typically picks a specific pathway. Like it'll have high weights in some places and not really use the entire model. Like some of the model will remain underutilized and it will just memorize the data by exploring a specific pathway to the end, and it'll just say this works, so I'm going to go with it. Dropout, what we say is instead of just picking one pathway through training, we randomly delete some of the nodes every iteration of training. So every single time we do a forward pass, we're going to randomly delete some of the nodes. And by doing this, what we're actually doing is making it harder for the model to train. Basically, the model needs to solve the same task with less resources. Obviously, during inference time, when we actually use the model, we'll be using the whole model. We're not going to be randomly deleting stuff. But during training, it seems that dropout really helps with overfitting by randomly deleting some of the layers as we go. This, again, just helps with the overall generalization of the model, and nn.Dropout is how we can implement that, nn.Dropout. This is dropout for the linear layers. There's also Dropout2d for convolution layers, but we'll kind of leave that aside for now. In the dropout, we do need to provide the probability. Remember, this is random. So if we say p is 0.5, then every step, roughly 50% of the nodes, will be dropped out on a specific layer. And so that's what we'll be doing. Great. So now that we have kind of put together all of these pieces, what we need to talk about is the AlexNet model. So the AlexNet model was basically the first major convolutional neural network that did amazing on the ImageNet task back in 2012, I believe. And so we'll be implementing the AlexNet model because it's very simple and should give you a good idea of how we build convolutional neural networks. And so this picture looks a little bit daunting. So let's go up to here first. So this is the typical structure of a convolutional neural network. What we do is take an input, do some convolutions, and create feature maps. And then we do subsampling. Subsampling is typically average pooling or max pooling. So there you go. So it does some more compression. Then you do some more convolutions. Then you do some more subsampling. And you just do it over and over again. And then you flatten your data and provide it to our fully connected layers for the purposes of classification. So what you're seeing here actually is the pattern that as you go through the model, the space, the resolution of the image becomes smaller and smaller. So notice how the height and width continues to get smaller as you continue through the model. But the width, or not the width, but the number of channels, or the feature space, increases. So as you go forward, notice that you have one channel here, and then we went to 4 channels, and then we went to more, and then we went to more, and you just keep doing this over and over again until you get to the output. So we get low resolution, lots of low resolution features extracted from our image. And this is the typical structure of convolutional neural networks. And so you see the same thing happening here. We have a large image, and as you go forward, you have you start with a 224 by 224 image. We end up with a 13 by 13 at the end. And notice that there's 3 channel input here because there are 3 channels, RGB, but we have 128 channels over here. So there we go. You also notice one other thing. Notice that there's 2 branches. You have this upper branch here and this bottom branch here. This is actually just one neural network, but due to GPU memory limitations of that time, it says it right here, explicitly showing the delineation of responsibilities between the 2 GPUs. Basically, they split the model between 2 GPUs to be able to actually train it efficiently. But that's basically it, nothing crazy. So all of the entire model I'm about to implement, I'll be kind of writing numbers down, but all the numbers I pick came from this paper. So I'm just doing what they did, just to keep it simple. So we're going to do class AlexNet nn.Module def init self classes is 2. So we're going to be doing dogs versus cats. So there's going to be 2 output classes, and dropout p is 0.5. Super dot init. So there we go. There's our start of the model. So we're going to do self.classes is classes, self.dropout p is dropout p. And now we're going to go ahead and define the feature extraction phase of our model and the classification head. So the first step is, the feature extraction, which is done via the convolution. So we're going to do self.feature extractor is nn.sequential. So sequential is an easy way of just stacking together a bunch of layers together and just treating it as a single forward pass. Just makes our life a little bit simpler. So the first one's going to be nn.Conv2d, and it's going to have in channels equals 3. Out channels is going to be 64. Kernel size is 11. Stride equals 4, and I believe padding is 2. So there is the first convolution of our neural network. After convolution, we're going to do a activation function. So like I mentioned, ReLU seems to work really well for image processing tasks. So we're going to be going with that, but you can experiment with other activation functions depending on what you're trying to do. Next, we're going to add in a pooling. So nn.maxPool2d kernel size is 3 and stride is equal to 2. Again, where am I getting these numbers from? I'm just following the paper, so nothing crazy. And then nn.batch norm 2d num features is 64. Why is this 64? Because we have 64 output channels from this convolution. So this batch norm is expecting 64 channels. And there we go. There is the first set of convolutions in our model. And all we're going to do is repeat this chunk a couple times, which is different numbers. So we're going to go ahead and copy this. So 2, let's see, 3, 4, 5. There's 5 sets. In this case, now this will be 64 here. And we're going to go from 64 to 192 with a kernel size of 5, a stride of 1, and a padding of 2. We're going to keep the ReLU activation. We're going to have another max pool with 3 and 2. And then this will be 192. That means the next input will have 192. And we're going to go up to 384 in this case. We're going to have a kernel size of 3, a stride of 1, and a padding of 1. Again, a ReLU, same max pool, but this is now going to be 384. In the next one, we're going to again go from 384, and we're going to go up to, or in this case actually, we go down to 256. Kernel size 3, stride 1, padding 1. We're going to keep the ReLU. In this case, we actually don't keep the max pool, so they don't do the max pooling in this specific layer. So there we go. Batch norm 2D, this is going to take 256 input. And then the last chunk will take 256 in, 256 out. We'll have a kernel size of 3, a stride of 1, and a padding of 1 with ReLU, max pool, and then this will be 256. So this is our feature extractor for the AlexNet. Again, all these numbers were just copied directly from this figure or any information given down here. So there we go. We have our convolutional feature extractor. We will then do a, so this is the important part. So let's go ahead and write a forward self x pass. And we're going to do model is AlexNet. And we're going to do rand is torch.rand, create a random tensor, let's say a batch size of 4 by 3 by 224 by 224. And these are 224s because they told us that the image size we're looking for, or we're looking to do, is 224. So there we go, 224. And how did they come up with these numbers? It was probably a mix of experimentation, trying different combinations, and also just fitting the biggest model that they could on the hardware they had available then. So there's probably less intuition and more just experimentation of why these numbers were selected. So we can do pass into our, let's print our model out real quick. Let's put the pass back. There's our model. The stack of all of the layers we have. We still haven't finished the model. We still need to write the classifier, but this should get us started. And we can simply do, let's do x is self.feature extractor x. We can delete this. We can do model rand, and we can do dot shape. And oh, actually the shape wouldn't be here. We need to do it right here. Okay, print x.shape. And there we go. We've downsampled our image all the way down to 2 by 2. And that's basically it. Nothing crazy, down to 2 by 2. But what if I change my image size to maybe 300 by 300? Let's say I want to do a slightly larger image. Then this becomes a 3 by 3. So this image space will obviously change a little bit with regards to the resolution that we have, right? So the way we can deal with this is the adaptive average pooling. We can always ensure it goes down to 2 by 2. is the big idea. So we can do self.averagePool is nn.AdaptiveAveragePool2d, and we can say 2 by 2 is the size we want. There we go. And we can do x is equal to self.averagePool x. Print x.shape. 2 by 2. This means that if I decide to train a higher resolution image, like 300 by 300, it'll still be 2 by 2. This 2 by 2 will never change. And this 256 will also never change because I have a number, my output channels is 256. So this gives me a little bit more flexibility because I know exactly what the output will look like. So there's nothing too crazy happening. Now, the last part will be our classification head. Self.head is nn.sequential. We're going to do a nn.dropout, and it's going to be a dropout p. So we're going to start with a dropout, and once we have our dropout, we can then do our linear layer, nn.linear 256 times 2 times 2, because remember, this is going to now be flattened from a 4 by 256 by 2 by 2 to a 4 by 256 times 2 times 2. For the same reason in MNIST. If you remember again, in MNIST we had a batch by channels, which was 1 by 28 by 28. And we flattened this to a batch by 784, right? This is what we flattened it to. And because we did this, we can then pass the 784 length feature vector to our linear classifier. And that's the main idea. So in the same way, we're going to take our 256 by 2 by 2, flatten it, and then pass it to our model. So 256 times 2 is 512, times 2 is 1024. So another important thing to keep in mind, our first linear layer will have 1024 inputs. If we didn't do it, if we only use linear layers and not convolutions, our first linear layer would have had a 224 times 224 input, which is 50,176. So much larger than the 1024 that we are planning on passing in. So we're going to do 256 times 2 times 2 to a 4096. Again, this is just what the paper decided, so that's what we're doing. We're going to add a activation function. We're going to do another nn.dropout. Dropout p, and then we're going to do another linear layer, nn.linear 4096 to 4096, 4096 to 4096, another activation function, and then lastly nn.linear 4096 to the number of classes we have. In our case, it'll be 2. So our final thing will be x is equal to self.head x. So we can print x.shape, and we'll have a bug. Nice. 256 times 2 times 2. Let's see what's going on here. Oh, yes. Print x.shape. We still didn't flatten it, right? We still need to flatten this. We're going to do x is equal to x.reshape batch size minus 1. And let's do batch size is equal to x.shape 0, right? Let's store the batch size up there. And there we go. So our final shape is a 4 by 2. So we passed in a 4 by 3 by 300 by 300. And our final output is a 4 by 2 for the 2 classes that we care about. And so this is effectively our AlexNet model implemented very simply in PyTorch. And we're going to return x. And there we go. These are our outputs. All that's left to do now is to train our model. So for the training of the model, we need to first define our data set. So path to data is, it's going to be // data dogs versus cats. That's where I stored my data. Normalizer. So this is where we'll be using a little bit of the Torch vision stuff that I mentioned. So PyTorch has a package called Torch Vision that does a lot of the Torch Vision stuff for you. And so we're going to be using some of them. The first one is the normalizer, right? We need to pre-normalize our data. We do, again, incorporate these batch norms in here, these batch normalizations, but these batch normalizations will be done, will have to be trained concurrently with the model, right? They'll estimate what the mean and standard deviation is after these layers, and what's the mean and standard deviation after these layers, and then the mean and standard deviation of these layers, and so on and so forth as we go forward. Again, remember, the batch norm was not in the original implementation of AlexNet because batch norm didn't exist when AlexNet came out. I just added it in because it's important to modern neural networks. And so but we do need to pre-normalize our data, right? And so how we normalize data in images is basically someone has gone in and computed what is the mean and standard deviation of the red, the green, and the blue channel, right? The R, G, and B. So what's the average R channel across a lot of images? What's the average G channel? What's the average B channel? What's the standard deviation of the R channels? What's the standard deviation of the G channels? What's the standard deviation of the B channels? Someone has already done the work and computed what these averages and standard deviation should be. And these are typical constants that you'll use all the time. And these are the ImageNet constants. So someone has computed ahead of time what they are. So if you're working on images that look like the ImageNet images, you're free to use these. These work really well. If your images don't look like the ImageNet images, like if you're working on MRI images or some weird medical thing or whatever it may be, if your images don't look like that, then you have to actually go in and calculate your own normalization constants, but that should be pretty easy. There's plenty of ways to do that. So there we go. That's our normalizer. So we need a couple of transformations on our data. So let's start with the first one. Train transforms is equal to transforms.compose. And what we're going to be doing, transforms.compose allows us to stack a sequence of transformations together. The first one is going to be, like we saw earlier when we did the data sets and data loaders, all of our images need to be resized to the same shape. Otherwise, it doesn't work out. We can't stack images into a batch that are different shapes. And in our case, these are pictures of dogs and cats taken with different phones and cameras. Everything's a different shape. Some are landscapes, some are portraits, some are whatever they may be. So we just need to make sure we transform them to be identical. So we're going to do transforms.resize, and we're going to resize to 224 by 224. There we go. The second one is, this is more for the purposes of, again, regularization. So we talked about how we can do weight regularization, we can do dropout. Another one are random transformations. So you can imagine it this way. If you have data and your model has a tendency to overfit or memorize the data, why not make the problem a little bit more challenging? And so one example of this is random flipping. If you have a picture of a dog and you flip the picture of the dog horizontally, it's still a picture of a dog, it's just flipped. But it is a slightly different sample than the original data you're working with. So random transformations are a great way to help your model generalize, because it's going to see the same data, just maybe in different colors or different orientations or all sorts of transformations. We're going to keep it simple today and just do a random horizontal flip, but there's other transformations. There's an entire documentation with literally hundreds of transformations you can pick from. We're going to do transforms.random horizontal flip. There we go. And then we have transforms.toTensor. We need to make sure we convert our PIL image format that it will be read in as to a PyTorch tensor. And then lastly, the normalizer, right? We want to normalize our image with these mean and standard deviation constants. And the reason there's 3 means and 3 standard deviations is because there's 3 input channels. If you're working on a different image format, like satellite images typically might have 7 or 8 hyperspectral bands. In satellite images, you'll have 7 or 8 means and standard deviations, just 1 per channel. You just have to pre-compute them by yourself. So these are our transformations, nothing crazy. So we can go ahead and now just build our data set. Our data set is the image folder. We'll be using image folder, path to data, and transform equals train transforms. And there we go. So we can do for sample in dataset, print sample and break. And we can see we get an image here, and we get a label, right? Is it 0 or 1 for dog or cat? So nothing crazy. And we've already seen the image folder earlier if you did the datasets data loaders tutorial. We need to do one more thing. I'll just copy this in because no need to type it. There's nothing happening. I'm just splitting my data into train and test splits. I'm keeping 90% of the data set for training, and then the remaining 10% for testing, and then I'm just splitting the data set up into train and validation. So if we take a quick look, print train data set, and not train data set, but rather the length of the training data set, we have about 22,437 images for training, and should be about 2494 images for validation. So there we go. Those are our images ready to go. So all we have left to do is to write a very simple training script, and we'll be done. So we're going to do device is equal to Cuda, if torch.cuda.isAvailable, else CPU. So you really don't want to be training models like AlexNet on the CPU. It will be very slow. And the convolutions are a really good example of where GPU parallelization really matters. In the models we've done so far, the toy models on MNIST, you don't really see the benefit of a GPU versus a CPU. You will see the benefit here. So let's go ahead and do a model. Is going to be our AlexNet model. I think the uppercase N. And we're going to say model is equal to model.to device. We're going to put it on the GPU. Epochs is 5. We're going to train for 5 epochs. The optimizer is optim.atom. We're going to use the atom optimizer, and params is model.parameters, right? We're going to train the parameters of the model with a learning rate of, let's say, 0. There we go, some learning rate. The loss function, just like before, will be nn.crossEntropy loss for the purposes of classification. And then batch size is 128. There we go. Now we have to build our data loader. So train loader is going to be a data loader around our train data set with a batch size of the selected batch size that we picked. We're going to make sure we shuffle the training data, and we can do num workers is 8, right? So there's a couple extra CPU cores there helping along. Then val loader is going to again be a data loader test or val data set. Batch size is batch size. No need to shuffle in the validation set. And again, num workers is 8. So let's go ahead and write a training script. So we're going to do def train. To the training script, we're going to provide a model, a device, a epochs, a optimizer, loss function, batch size, train loader, and val loader. So there we go. That's everything we need. So just to keep things very simple, we're going to log the training. So we're going to do log training, and we're going to keep track of the epoch, the training loss, the training accuracy, the validation loss, and the validation accuracy. So those are, very simple dictionary. Just keep track of that stuff. So we're going to do for epoch and range epochs. We're going to print. Training epoch and let's do epoch plus 1 because it'll start at 0, so it'll start at 1 now. So it'll go from 1 to 5 rather than 0 to 4. And for this epoch, we just need to keep track of the training losses, training accuracies. Let's make 2 empty lists, and then validation losses, validation accuracies. There we go. And so now we can do model.train, set the model to training mode, and we can do for image label in tqdm train loader. Right? For each of these, we're going to make sure the image, just like before, the image and label are both on the device. Image label.to device. Make sure everything's on the GPU. Optimizer dot zero grad. We're going to go ahead and zero out our gradients. And then after we zero our gradients, we can do out is equal to model dot forward or just model image. Okay, passing our images in. Now we calculate our loss. The loss is just the loss function that we defined, the cross entropy loss between the output and the label. And training losses dot append loss dot item. Right, so we can keep track of that stuff. Similarly for accuracy, so we've done this before, so I'll kind of just go through it. Torch.arg max axis equals equals 1 or minus 1, it doesn't matter. Basically, whatever is the highest probability thing will be our prediction. So that's what we're doing. We're just grabbing the highest probability index. So argmax, our accuracy is going to be predictions equals label dot sum. Just find out where do our predictions equal the labels, add them up, and divide by the len of prediction. So we get the % accuracy of how many things are correct. And we can do training accuracies dot append accuracy dot item. So there's our training, and then we update our model, right? Loss dot backward optimizer dot step. Second stage. The second part will be almost identical to this with just a few caveats. So we're going to do model.eval, right? We're going to throw our model into evaluation mode. Instead of a train loader, we're going to be doing the val loader. We're going to be looping through our validation data. There is no zeroing of gradients in this step. There's also no updating of the model for the purposes of validating the thing. When we pass our data through the model, we can do with torch.noGrad, because we don't need to compute gradients for any of this. And then we don't want to store these in training loss, but rather we want to train them in validation losses. Validation losses, and then validation accuracies. And once this is done, I'm just going to copy this part in so I don't have to type it all. It's mostly just printing out the console so we can see how things are going. And there we go. We're going to go ahead and for this specific epoch, we're going to average up the training loss, training accuracy, validation losses, validation accuracies, store them in our log, and then print them out. And then at the end, we will return the log training and the model. So let's go ahead and train. We can do logs and model is equal to train, where we pass in the model, the device that we picked, the epochs, the optimizer, the loss function, the batch size, the train loader, and the val loader. And we can see now if there's any errors. Here we go. Missing one in torch.argmax. This needs to, we then provided the out. So out and out. And there we go. Our model is now training. So again, this is a very, very simple example of a convolutional neural network. You can see we're already at 75, 76% accuracy for this specific model. And yeah, so that basically wraps it up. Just to give a general idea though here, and this is very important, like why do we use GPUs instead of CPUs? So we're gonna say device is CPU. You'll see the training's taking about a minute an epoch. Still not the worst actually, but obviously significantly slower than what we had just experienced with the GPU, right? So that's the important part. Either way, this kind of concludes what I wanted to show. So I'll do a quick recap one more time. Basically, we talked about how convolutions allow us to do frequency domain operations in the time domain for a cheaper cost, and convolutions have existed basically forever. They've been used for signal processing for a very long time. Convolutional neural networks basically is just a filter bank. So instead of just one filter, we're going to be applying multiple filters on the image. It also adds a hierarchy of filters with nonlinearity, because we have convolutions plus a nonlinear layer plus another set of convolutions plus another nonlinear layer, so on and so forth, stacked on top of each other. And the depth of that model seems to help quite a bit to do things like image classification. And most importantly, it allows us to train neural networks on large resolution images without as much of a memory cost, because we're not having to flatten an image and lose all of that spatial correlation that the convolutions can extract. There are a couple limitations to convolutions, as in they are local operations. They compute things like details in local areas, like it's good at picking up texture and things like that. It doesn't have as much a global understanding of the image, and this is why the vision transformer is super cool, and while we'll be exploring and reproducing that in a future video. But for today, this is basically the setup. Convolutions are a bread and butter mechanism for image processing and signal processing in general, and the novelty of the convolutional neural network and what was shown in the AlexNet model is, instead of me deciding ahead of time that, oh, I want these specific filters, like I want a low pass filter and a high pass filter and a difference of Gaussian filter and this filter and that filter, and I create my filter bank, grab all those features from my images, and then pass that to a classification model, why not train it end to end? Why not also train the filters themselves along with the classification model completely in one go? And that's the novelty of convolutions. They're used in images, they're used in audio, they're used in point cloud data, they're used for MRI stuff, they're used for videos, they're used effectively everywhere. Transformers have come quite a long way and actually beat convolutions in a lot of important computer vision tasks. But convolutions still have the benefit of not needing nearly as much data to get almost as good performance. So they require much less data than transformers do. And so, yeah, that sets it up. Next time we'll be looking at sequence modeling. So we'll start looking at recurrent neural networks, but I'll leave it here. If you made it this far, thank you for listening. And please share your feedback. Let me know if there's anything else you want to know, and I'll see you in the next one.